Welcome to the Earthworks podcast, where our team will share the jargon of carbon with many of the turf friends we've met over the past 35 years.
Hi, everybody. This is Joel Simmons, and this is another Earthworks podcast. And we have back our favorite guest, back by demand, because everybody always calls me and says, "Hey, is Lawrence going to be back on the podcast again?" And I've unfortunately we have blown his head up to a point where he actually really thinks he's of great value to us, but he is. So it's Lawrence has been you've been with our team for a very long time. I mean, you were working with Jerry before even came on board working for Jerry. So I mean, working with us, but Jerry Brunetti, who of course is my co-founder, who we lost to cancer a number of years ago. But you guys worked together prior to ever having any involvement with Earthworks, and you've been with Earthworks as our chemist now for, well, the better part of 10 years, right? Because you came on quite, I mean, Jerry's been gone for about 10 years. So you came on board, and I quite honestly don't know what I would do without you. Lawrence is basically helping us keep our products clean, safe, and working properly. We tweak and fine tune things on a regular basis. For those of you who don't know, and most of you probably do, I consider Lawrence to be a world-renowned humic specialist, humic substance specialist. And he's told that story a couple of times on the podcast, but that really becomes the foundation of all of our Earthworks liquids. And that really, quite honestly, Lawrence, I mean, when we started working together and we were fighting stability problems, it was your work with humic substances that stabilized everything. And it was eye-opener to me. I mean, we were, many people remember we had as any product that is as complex and as big as the Earthworks liquids, and it's, 30 raw materials. What you did with bringing in that humic acids, humic substances, I keep saying that, sorry, bringing in the humic substances to stabilize and bring everything together allowed us to really kind of hold the diversity and the complexity of what these products are really doing, and that's why I think why they're so successful. But and I do want to talk to you a little bit about humic acids before we get on our subject. And today's subject is the biology of Thatch. So we're going to go through a little bit about what is the biology of Thatch and how how it works and how it happens, and we're certainly seeing a lot of changes in the industry about that. But I really want you to dive into what is the biological piece of that. But let me ask you this first. Humic substances, still to this date, and you were telling me before we came on air that you actually had a client that asked you to do the myths of biology, and they sent you a list of questions, and they were the same questions that you might have had 10, 15, 20 years ago.
Yeah. Yeah.
I mean, I go around the country and I talk, in the academy, and we talk about humic substances. It probably was one of the first really recognized carbon materials in products out there in the turf and ornamental industry. And still, I think there's a lot of mystery about. And I still see things like a lot of, and I'll mention no names, but a lot of products in the market that will list humic acids as derived from humus. Or I'll see humic acids at 85%. And you've taught us over the years, and we've listened well, that none of that is really possible, is it?
Correct.
So what's the myths?
What? Beg your pardon?
What's the myths?
Well, your 85% can be put on a label depending on which analytical method they choose. Because there's so many flawed analytical methods. You can, if you shop around, literally shop around, send your product to different labs until you score high, you have probably just experienced a lab who really doesn't know what a humic acids product is or an ingredient, because there's only one validated analytical method out there. And there's numerous methods being used by these labs. So that gets really confusing for the customer, because everybody thinks humic acids are humic acids.
Yeah.
That depends on the analytical method and even the proficiency of the laboratory that you send it to. So it's not straightforward.
So, but would the states in registration accept some of these off-the-wall analytical methods, or
Unfortunately, they do. Yes. We developed the standardized method in 2016, if I recall, and then that became an ISO standard in 2018. I made presentations to APCO at their laboratory services committee level and labeling committee and that sort of thing, introducing them to this brand new method that is validated. None of the others are validated. But even though it's been a long time since I made
yeah?
those presentations, they didn't necessarily run with it. And
Explain the validation process. Explain what you mean by validated.
the the ISO 19822 is the
Write
only,
that down.
yeah, ISO 19822. I have written that down a lot of,
And I've heard it from you 100 times.
yeah, uh, was validated through what's called an interlaboratory study. Various laboratories throughout the whole world, not just United States, participated in the study. If I recall, it was right around 14 laboratories. So if you send a method of analysis out to 14 laboratories through the whole world, and they send back the data to me, for example, I go through the data, statistically clean it up, and then I now have some solid numbers because I've got 14 labs participating in this doing the same procedure.
Now, what
That
happens if one or two of the labs is completely off in the left field?
that happens. That's normal.
Yeah, that's part
So
of the statistical
I would contact
determination.
them. I
Ah,
would contact them and I would say, look, here's where you are compared to everybody else. You need to review what you're doing, and
mm,
I'm happy to help you out step by step. Usually it was drying or ashing or something like that.
ah,
Nothing directly from the method of an analysis. It was really sample preparation
gotcha.
mostly was the problem.
Interesting. Yeah. So, and the method you're talking about is approved by the Humic Products Trade Association, the HPTA.
Correct.
Yeah, and that's when we started this process, we went through all of that
Hmm.
and found some things that we weren't real happy with, and with your guidance, we were able to make a lot of changes. And I've said this to many clients, and I probably said it here on the podcast, but with your guidance again, because you're looking at all the humic acids going through. I don't know how many times you've come to me and said, "Hey, I just found a really great humic acid that we should try to play with," and then there it goes. We tweak and tweak and tweak.
Mhm.
But it really has become quite interesting. So what you're saying is that even though a company might say it's 85% humic acid, I mean technically they could be legitimate based on the laboratory that the state has allowed to use. But I mean, so following your methodology, is there a way by which a consumer can truly know that what a manufacturer is offering is a true humic substance?
I strongly believe that whatever you're purchasing has to be traceable back to a member company that manufactured the raw ingredients or something like
Yeah,
that. They have to get their raw ingredients somewhere. And if that manufacturer or supplier is a member of the Humic Products Trade Association, then it's very likely that that is a legitimate source. So there needs to be traceability in order to really
gotcha.
know for a fact that it actually is a legitimate material.
What about, these labels that we say derive from humus? I mean, that's always baffled my
That
clients
that
and
doesn't
us.
even comply with regulatory
Okay, so
standards.
it's just wrong.
Yeah, yeah. The
Okay,
regulatory standards say it can be derived from leonardite and all the various names of leonardite,
right.
oxidized lignite, that sort of thing. But it does not include humus in that list. It's not there. And it's pretty good reason for that.
So if we see that on a label and it's been state registered, how does that happen? I mean, I
It
get
it
black eyes all the
unfortunately
time from the
happens.
states.
Not all regulators are up to date on
Yeah,
every aspect of their work. I mean, there's other things they may be deficient in also, but specifically addressing humic materials, They're very confusing.
Yeah,
People really don't understand them, and regulators at a certain state may not even care.
yeah.
They'll just go ahead and register it no matter what claim you made. But other states like California, Oregon, Washington, your favorites,
Yes, everybody's favorites.
are very particular
Yeah, yeah.
about
It's
what
yeah,
you say
they're
about humic materials.
we'll say they're thorough. They're very thorough.
Very
What
thorough.
about lignosulfonates? How do they get through
Lignosulfonates are dark. They look like humic acids
physically?
physically. They have some chelating ability, but nowhere near the ability of humic substances. But nonetheless, they do have some benefit. The big giveaway is, first of all, the sulfur or sulfide smell that comes off of
Yeah.
them. And that's a big giveaway. And if you are suspicious whether you have a humic acid or whether you have a lignosulfonate, very simple procedure. Just send it out and get it tested for sulfur content.
Yeah, it's funny you say that because, and I don't know if you remember this, but a few months back, I was with a group, and they shared with me their, I think they were calling it a fulvic, and I said, Lawrence, is there a quick way to determine if this is real? And it was in a little Ziploc plastic bag, and
Mhm.
your response to me was, open it up and smell it. Does it smell like sulfur? And I opened it up, and I got this massive woof of sulfur, and I'm like,
Yeah,
whoa. Yeah, I
yeah,
mean, and of course, I smell the raw materials that we put in, and we've never smelled sulfur, but that
yeah,
that really drove that home. And and I wasn't trying to be, I wasn't trying to be a jerk, but this was a group that I was working with, and I said, I think you guys might be getting a bill of goods here because this is not humic substances, this is lignosulfonates, and they didn't even know. And that goes back to what I'm trying to get at here is that a lot of people don't know because
right.
we're told that, oh, this is fulvic acid when it's not fulvic acid at all, which
Mhm.
is interesting. All right, in a minute, if you can do this, and I'm not sure you can, in a minute's time, tell us exactly what a humic acid is good for and why we use them.
Humic acids are very good for soil conditioning. They provide the conditions for microbiological activity, which is very critical to metal ion exchange. And it's really a great physical and chemical and biological conditioner for soils. That's where you want to position it as a
Wow, that was
soil
actually
additive.
less than a minute. I'm very impressed. Thank you for that. Let's talk about why we're here. I want to talk. I mean, we've been talking on the podcast and obviously a lot of conversation in our industry about organic matter. There's a lot of conversation going on in the industry. There's a thing going on that you may not be familiar with in the turf industry where they're slicing inches or centimeters and measuring organic matter at certain levels. But what I really want to talk about, and you and I have been working on a project where we're doing a talk on the biology of thatch. I want to talk about how thatch comes about. I want to talk about the difference between, good organic matter and bad organic matter. And I want you to go through step by step your approach to this green, brown, and I keep saying black, but we're calling it dark organic matter. And let's start by talking about first and foremost, when you send a sample into the lab, they test organic matter. Walk us through how that test is done and what it really means. The burn test.
When the lab receives the sample, they try to pull out any kind of obvious things like roots or anything that's recognizable,
Yeah, they
essentially.
actually screen it. They put it through a screener.
Yeah, that the effort is made. Now, a little bit of that still going to slip through,
Right.
but it's debatable whether it has a big impact or not. It's not perfect, but it's a start. And they try to remove anything that they don't think is really what they're trying to test. Then the next step is to put it into a muffle furnace at 500 degrees centigrade, which will burn off organic matter. It'll volatilize it. It'll turn it into carbon dioxide, a gas, and woof, it goes up. So when they pull the sample back out of the muffle furnace, it's got less weight, right?
Right.
So
So they weigh it beforehand in a
yeah, weigh
crucible,
it
and then
before.
they burn it, and then they weigh it again, and the difference is the organic matter
So the
percentage.
difference in weight, which is called loss on ignition, LOI, is their definition of organic matter.
And most labs will even consider that humus. Although I question that, and I would ask your opinion on this, but I mean, to me, I don't know if that would necessarily define humus as we know it from as we're going to discuss here, as humus from a biological standpoint. But I mean, is that can you look at your soil test and say, oh, I've got 2.5% humus and feel comfortable with that, or are we kind of in a gray area with that number? If you
Uh,
follow what I'm asking.
I think so.
Okay, good,
Um,
because I'm not very clear.
uh, Humus has been well defined by numerous organizations. The one that's generally accepted is the definition that's out there that put out by the Soil Science Society of America. Good as it gets.
Yeah,
Okay. Their definition is organic matter that is fully decomposed and partially decomposed and
interesting.
undecomposed.
Right. So you got a number of positions of which this organic matter lies within the biological profile that we're going to talk about here. But let me again set the stage a little bit. We've been talking on the podcast with a number of folks, particularly John Riley, our friend down at Longboat Key, and one of the things that's really happening in our organization, or I should say, in our industry, is that there's a big debate over the process of aerification. And aerification has always been there to open up tight, compacted soils, but it's also been there a lot of times to remove the most ligneous material, which we'll call thatch. And I think I can define thatch by an imbalance of carbon to nitrogen, or perhaps even, without criticism of synthetic fertilizers, an overuse of synthetic fertilizers. So what's happening is that we apply, I'll use urea as the example, a lot of urea. We burn out the available carbon in the soil, so microactivity is now running slower and slower and slower. So the digestion process is weaker and weaker. The roots continue to grow. And that's what we look at as thatch. And any golf course superintendent or sports turf manager can feel that. They can hold that first inch or two and feel the ligneous nature of that. That's what they're seeing. And then, of course, aerification became a necessity because we need to physically remove that thatch. The trend is, and I can say comfortably that we've been very involved in moving this needle. The trend is to work this now biologically. And again, that's why you're here. We want to be able to work this digestion process. So if we can take this, and the analogy, and tell me if you think I'm off base here, but the analogy I often will use is it's like a little compost pile in the soil. You think, you start with a compost pile of leaves in the fall, it's, up to your neck. And then by next summer, it's about 5-6 inches high because microbes have done their job and they've digested all that ligneous material into a tiny little pile. And after a year or three, depending on where you are in your power of biology, you've got this beautiful compost. That's what we're trying to talk about when we talk about the biology of thatch. So you have come up with something that we think is quite brilliant. This concept of green, brown, and dark. And I believe we did talk about this once on a podcast, but I'm going to reiterate. I'm going to revisit this because it's still pertinent, and I think it explains the trend of why we might be moving more to needle tines and deep tining, and less to pulling cores that remove organic matter from the soil. Clearly, if you have good organic matter, or what we'll call humus, you don't want to remove that. You want that in your soil. What you do want to remove or start to digest is this very ligneous material of thatch. So there's my dissertation. I will now properly shut up and let you take this over, if I'm capable of doing that. And most people are laughing right now. Talk to us about the three stages: green, brown, and dark.
It's those are terms actually from regenerative agriculture. Uh, it's not a formalized thing at all. It's
No.
just
Yeah.
the way regenerative farmers and practitioners refer to the various stages of the organic matter that's in soils. The green originally came from literally putting green manure into the soil as a starting point,
Hmm.
and that comes from cover crops in regenerative agriculture. And in regenerative agriculture, we have the same thing you have. It's called no-till, where they do
Yeah.
not plow and they do not disturb the
And
soil.
it's quite popular now, right? I mean, it's really the direction
Uh,
that regenerative
well, Gary
agriculture.
Zimmer said you got to look at the back of the No-Till magazine. It's a national magazine. He said the number one advertisers are there are deep rippers and aerators.
Oh.
So I thought, okay, I got to look this up, and
Is
there
that
it is.
true? I didn't know that.
Yeah, it was. Yeah, they're providing a lot of advertising to No Till magazine.
That's
You
interesting.
guys
Why?
need air, and you need it so bad. So it also the green organic matter came from literally plowing in or incorporating green or succulent plants, a
Yeah.
cover crop in the case of regenerative agriculture. Now, to apply that same thing to turf, it would apply to the ligneous material that's left over by the root system, which
Hmm.
also includes cellulose and hemicellulose. So there's more than just lignin in the root system. In a natural system, when a root dies back, it will decompose and break down in the presence of oxygen and microbes. Unfortunately, in some turf systems, they lack some air, and they
Right.
also lack carbon sources for the microbes. The microbes require very simple carbons at that stage, i.e., sugars. It comes to mind right away, carbohydrates. Well, those can be supplied by the plant. And the plant roots actually will exude those materials and get that process going. Now, so that's what they call the green stage. So you got some pretty crude organic matter in there that's not broken down at all. And then when
This would explain, and I didn't mean to interrupt, but this would explain why if you're not doing anything to push your grass, like your home lawn, for example, you typically aren't growing thatch, right? Because you're not throwing that seed end ratio, and your plant is providing enough carbohydrate to feed microbes to digest the I'm saying ligneous, but obviously incorporating a lot of different
Mhm.
lignin type materials. But is that a decent analogy? I mean,
Oh
in a
yeah, because roughly 30 to 50% of the carbon, the photosynthetic carbon that the plant makes from sunshine goes down into the root system in the form of exudates to be released in the root system to provide energy
right.
for these breakdown processes. It's actually mineralization of the root is what
Yeah.
it's trying, or dead root, which is
Yeah.
trying to achieve. Now, oh, sorry.
Let me take you back one step because recently at an academy that I did along with Kevin Hicks, he brought into an analogy that I thought was pretty interesting. He brought into the analogy, and I know you can talk about this, of the dust bowls. You know, the 30s and 40s when the Midwestern high, organic soils were basically being destroyed. And, the Dust Bowl came. Talk about what that means. What actually physically and biologically and chemically happened to create the Dust Bowl? And I think the analogy, you can see where I'm going with this. I think the analogy is pertinent to what we're talking about, the destruction of organic matter.
That's exactly what happened. Every management thing they did just
Yeah.
destroyed the natural organic matter and the natural carbon cycling process in those soils. Just stopped it. The soils lost their ability to hold water because organic matter provides that thing for sure. The soils lost their ability to exchange nutrients efficiently, so the plants didn't grow too well. The root systems did not develop well, so there wasn't really much there to hold that soil in. And when they lost their aggregates, which is directly a result of proper organic matter management, then there was nothing to hold the soil and it just took off.
And a lot of plowing going on, so really physical damage to the soil. I think it was the beginning
It
of
was
the
deep
yeah,
plow.
deep plowing and the
Yeah.
beginning of a lot of synthetic fertilizers were coming into fashion where before they hadn't
Yes.
really been synthetic fertilizers. So again,
Mhm.
if you talk of nitrification, that nitrogen has to be broken down by microbial activity. Those microbes need available carbon in the soil, food sources, and they're literally being burned up on a regular basis. And then again, that's really the genesis of how we create thatch. I don't know that I've shared this with you, and you not being in the golf industry, but in the 90s, it was vogue to grow in a sand-based golf course green using in a short period of maybe 5 months or less 10 or 20 pounds per 1,000 square feet of synthetic nitrogen. And
Mhm.
one of the things that grew really, really well was a really big fat layer of thatch. And then, the construction team would pack their bags, they would go, the architect would leave, and the poor superintendent is standing there holding the bag, and what they left him was, 4 inches of very undigested ligneous kind of material. And that's been, traditional. That's changing. I mean, we are definitely seeing carbon-based fertility really taking hold, and I take some credit for that if I can. And Jerry certainly would if he was sitting here. But I think, this is where we've been, and I think the trend is to understand that there's a biology of this. So, let me get back to green. There's a lot of things happening in the green. In our case, it's root systems, but you also talked a lot about the chemistry that's coming in from the plant, and then all the cofactors that are in the soil that are helping, that first stage of green. What makes the green break down, and it seems to be moving in multiple directions as you described it to me the other day.
I think the general perception is that it's bacterial breakdown, but that only accounts for about 1/3 of the critters that are actually involved in breaking down. Most of the process of breaking down the lignin portion is actually driven by fungi,
Hmm.
and fungi need kind of different conditions for survival than bacteria do.
What are they?
Primarily, they need a buffered soil. They
Yeah.
need something that's not crazy pH, either too high or too low. And the way we achieve that from a product standpoint is to put in a pretty good dose of humic acids.
There you go.
They have an extremely high buffering capacity. They also have the ability to calm down what's called chaotropes. Chaotropes like nitrates and sulfates and chlorides. All these things have a tendency to disrupt the structure of water and water usage. And these microbes really need all the efficiency that they can get. So and that's primarily achieved by making sure we have a bioavailable source of calcium that drives the whole system. Regenerative agriculture is really built around calcium rather than nitrogen, phosphorus, and potassium. It's just the total opposite. They build and balance around calcium. Once that bioavailable calcium is there, it also stimulates exudates, plant exudates, probably because it's actually balancing the nutrient system and allowing the microbes to grow efficiently. And when I say microbes, I mean both bacteria and fungi, and more fungi than bacteria. And if you have a high salt condition and a low pH, the only thing that survives under that are bacteria. The fungi do not like those
Yeah.
conditions.
Yeah. I recall my early years with Jerry, and when we were starting to do development, that was why he was so adamant about having so many raw materials in there, because we don't want to feed just bacteria. We want to feed bacteria, actinomycetes, mycorrhizae, other forms of fungi. I mean, that's essentially, and now that you've taken over a lot of that formulations, I mean, is that not what we're doing by having multiple forms of food sources? We're feeding multiple populations of microorganisms.
Well, when we put humic materials in, we are not feeding anything.
Right.
Nothing.
That's important to
That's
understand.
that's a that's a broad misconception.
Yeah.
It's not an energy source for microbes at all. It is creating the conditions for these exchanges. There has to be a lot of exchanges taking place. And enzymatic activity is extremely important in biological reactions. If we didn't have enzymes, we wouldn't be able to blink our eyes. So enzymes are there to really, really make this run efficiently. And humic materials stabilize enzymes. They stabilize proteins. They stabilize amino acids that are there as a nitrogen source for the microbes. So when you see humic materials going into a system and you're getting more whatever production or degradation of root systems, you are not feeding anything. You are
Right.
providing the conditions for these reactions to take place.
And we're still seeing in the marketplace products that are claiming to be carbon based, and all they have as a carbon source is a humic, which is wonderful, but it's not feeding microbes.
No, sugars do.
Yeah, and kelp does, and fish does, and fermentation solids do, and seawater extracts do. I mean, the things that we've been working with over the years
Mhm.
feed a broad spectrum of soil biology, which is really the key thing. I mean, we're seeing a surge of things like straight molasses, which we had some folks on a number of times on the podcast talking about that and how it feeds a very narrow band of mostly bacteria, right? And
Yeah.
if we're trying to dissolve thatch. Now, the other thing that's really vogue right now, and I don't know, you and I have talked about this, but now there's a surge of people coming out with biological digesters. And again, probably great, but if the environment and if the food source isn't there for them to really proliferate, can they really be long-term successful?
Unlikely.
Yeah. I mean, again, we talk. You and I have talked about it, and we've certainly talked in our on our team. We love this direction, but I think it needs to be all put together. And again, I think it goes back to the feeding process that allows it to go. Again,
Well, like in your products, there's molasses in a lot of those products, but it's in single digits.
right.
You
And
know?
there's what, 4 or 5 other sugars that we've used.
Oh
So
yeah,
not
and the
just
amino
molasses.
acid, the amino acid complex coming from
Yeah.
fish and kelp. Yeah, there it just takes a lot more than just one ingredient because you need diversity in order to support this biological system that's in this case there to break down thatch.
Yeah, exactly, which is important. And again, that was really what, Jerry his vision showed us back in the mid, actually he was probably doing this in the 70s, but I came along in the late 80s and, I'm some dumb kid who doesn't know anything, but that has some passion for this and that's really what we did. Let's go back to this. So we kind of let's finish up on green,
Mhm.
the green organic matter and make sure that we haven't missed anything. And one of the questions that I would ask is, how do you start digesting? I mean, the green would be the root system for the most part in turf. It would be the most long chain carbon. It would be the most ligneous material, although, lots of other things. How do we break that down? How do we get that to start moving into the brown stage that we'll talk about next?
It's broken down primarily by the enzymes that are generated by the microbes. For that very purpose. Lactase comes to mind right away.
Yeah,
These are enzymes that can break down lignin, but it's not that simple. You can't
never
just add it
is.
in. You can't put an enzyme in your product and say, "Here, this is going to work great." I mean, first of all, that enzyme needs to be replenished constantly.
Yeah. Or
This isn't a
generated
one.
naturally, which is what
Yeah,
we're trying to do. We're not
yeah.
trying
You
to
can't you
provide
can't
them.
dose it. You can't
Yeah,
dose it once.
right.
And the microbes are there providing it for free. You don't have to buy enzymes.
Shh, careful.
Okay.
But yeah, no, I mean, so
Regenerative farmers grow their own nitrogen.
yes, they
They
do.
become less and less
Nicely.
and less
Yeah.
reliant on nitrogen.
Talk
With
about how the microbes generate the enzymes. I mean, that's probably something that most people, will find new information. So the
uh,
enzymes are coming from microbial
yeah,
production.
and these enzymes are dependent upon cofactors.
Right.
They're either trace or ultra trace element cofactors, or they might be a micronutrient like boron or zinc, more some of the more common ones, or copper, especially copper. Copper and zinc are the two big ones, and manganese is extremely important
Yeah.
for this process.
Well, you've
And so
even taken it down for us, even to smaller elements. I don't like some of them I can't even pronounce. Berlin, whatever. There's a number of them we've talked about over the
well,
years.
this cycle is very dependent
Yeah.
upon nickel, but
There,
who
I
addresses
can I
that?
can pronounce nickel, but
Okay. Yeah, we definitely put nickel in the product. It's not going to show up on the label because the labeling law says you have to have so much in there before you can
yeah.
guarantee it. Well, okay. I
I
mean,
mean, you
one,
sent us a chart on C3 that had over
mhm.
70 trace elements, many
Yeah,
of
about
which
72 was it? Something like that.
72, 75, but many of them I can't even pronounce, and the numbers were so minuscule. Um,
Extremely low
yeah,
concentration.
and conventional wisdom and the naysayers are going to say, "Oh, there's only 16 essential elements, and all this is bullshit, and
Mhm.
you don't need any of that crap." But none of that's true, is it? I mean, these are
Well,
all
just
elements
for
used.
nitrogen fixation and utilization and even breakdown of this, there's also a need for vanadium and tungsten. Now,
Who would have thought?
that's not something we generally add because it's in our natural minerals.
Yeah,
When we get these things from natural sources, it's already there. But we nevertheless do analyze for it in case they're coming up deficient.
yeah. So by having those in products like ours or any products, I'm not trying to promote Earthworks necessarily, but having them in there, which is important to us, provides the support for microbial populations to generate the enzymes that they need to function in multiple levels, right?
The the enzymes are typically dependent upon some metal of some sort.
Yeah.
And some of these metals you've never heard of before. So,
And can't pronounce. Yeah, and it's, I mean, I show that slide that you put together, that page of 70 plus minerals.
mhm,
And and I've had a lot of pushback. The big pushback as well.
mhm.
If we were to tissue test any plant, would most of those metals be found in a tissue in a plant?
Absolutely. Well, probably more so in the root system. The root system is
Okay,
more
even
dependent
better.
on them.
Yeah,
Yeah, the root system is much more dependent upon these things, which makes sense. They're right down there, they're in the soil, and there's a lot of things going on down there in that
and they're
soil.
taking
You
them.
don't
Yeah,
necessarily send them up into the plant.
but if they're in the plant, I mean, the argument is, well, the plant doesn't need that. But why would the plant bring it in if
So
it
after
doesn't?
500 million years of evolution, someone's going to say that plant doesn't know what it's doing. Is that what they're trying to tell me?
I'm
They,
just
I
telling you
was
what I hear.
when I was in college, they said, "Oh, they plant can't tell the difference between potassium and rubidium and cesium, so they just take them all up." Well, what
Perfect.
if you find a gene specific to the utilization of rubidium, for example? I mean,
Right.
that's true. Here's a genetic commitment to taking this particular thing up that nobody talks about. That's an accident? I don't
Yeah.
think so.
Yeah. I was asked to get you wound up, and I think I've accomplished.
Well, what they do is these things you never heard of before will substitute for things you have heard of before
Yeah.
under stress conditions. That's where they do their work almost without question, almost without exception. So calcium will be substituted by strontium under stress conditions. You got to calm that calcium down sometimes. What if it's really hot out? Oh, by the way, when these plants are under heat stress, the amount of photosynthetic carbon that goes to the roots is now only 5%.
Wow.
You want to break down thatch in the summer? Good luck.
Yeah.
Mhm.
What if we have improved the biological environment in the soil? Well,
Doesn't matter. They're not getting those
they're
exudates.
not
They're not
getting the
getting that
exudates.
photosynthetic
Yeah.
carbon anymore
Yeah.
when they're under heat stress. So the best time to break down thatch is in the spring under
And,
ideal
and,
growing
and yeah,
conditions and
in
the
the fall.
fall under ideal growing conditions, as that's when the most synthetic carbon is going down
Yeah.
to that root system.
And that goes back to, we talk about this a lot. Set up the stage for June, July, and August. And that's
Yeah.
why we get a lot of questions about, when should I start using my liquid sprays? As soon as you break dormancy, start feeding that soil because those 2 or 3 months set the stage for 2 or 3 months that you're just basically holding your breath, hoping you survive. As we sit here on the 29th of July,
Mhm.
I'm sitting in my little office, and outside here, it's almost 100 degrees.
Mhm.
It's been one of the worst summers I've seen in a long time. It's been hot in the Northeast and many parts of the country, Kentucky, St. Louis, certainly the Mid-Atlantic, and it's been rainy. So we're setting ourselves up for a lot of disease issues. But
So these plants are going into survival mode. They're not
yeah,
sending hardly any root exudate
yeah,
carbon down there at all at this point. And one of the first things that happens is when they go in survival mode, growth, anything that has anything to do with growth pretty well gets shut down and
yeah.
they need to survive.
And that's why I use this word, and I'm not sure I've ever defined it well, but I use this word buffer, soil buffer,
Yeah.
and by having, an adequate level of available carbon, and those available carbons is really humus. It's not sugar necessarily. It's the soil carbon that at least provides moisture management, moisture holding capacity. It provides a buffer for temperature. It provides especially if we can get an ample amount of humate in there, we got an environment by which biology can still continue to proliferate in the worst of environments. We have checks and balances for pathogens, and maybe most importantly, it's these little critters that are helping break free nutrients that the plant's looking for, especially when they're under stress. I mean, isn't this time of year the time when the plant is calling on most nutrients because they're under such heat stress?
This is the time of the year when enzymatic activity is extremely critical. And this is the time of the year where these cofactors are definitely doing their job.
How can we improve that?
Improve
And how do we improve the environment by which those functions occur in the summer
by
months?
bringing in extremely complex inputs.
There you go. Thank you, Mr. Brunetti. That's what we do. Let's
Well,
let's
that's
go
the way.
to well, that's what he's
I don't
taught
know any
me and
other way
taught
to
you.
do it.
Yeah,
You can spend a lot of money trying to put 75 elements in a
yeah.
fertilizer, but if you can
Or
buy
let
it,
Mother Nature do it. Yeah,
if you can buy it in the form of a natural
yeah.
product, then
And
that's all.
we're describing C3, right? It's pretty much what we're.
Well, C3 really got me when I first started working for you because you can't even guarantee NP and K on a label with C3
No,
because there's so little of it.
I
Then I
know.
found out that this product greens up really, really good.
Yeah,
So
shocking.
can't be nitrogen, but it actually is. It comes from the amino acid content and the
Right.
kelp. There's things in there that can provide nitrogen through biological management rather than
Yeah.
straight mineral input.
And that's the other thing that you took and tested. We ended up with what, 25 different amino acids in that complex.
Yeah, I
And
was always under the
that complex
impression
is the foundation of all of our
I always
stuff.
thought there were only 20 natural amino acids. And
I remember you saying that.
yeah, I learned something about
Yeah.
that. Well,
What?
they're not all what's called proteogenic. Not all amino acids will generate protein. That's what threw me off. So
Right.
you have some amino acids in there that doing other things besides generating proteins.
And none of these are applied. They're all part of these natural products that we're
Mhm.
combining all together. So we have this
And if they're high
combination of
in
a lot of stuff.
proline, for example,
Yeah.
one of the amino acids, just pick one amino acid, let's say proline, and you've got it.
Yeah.
Hey, there's a lot of research on proline alone and how plants get through stressful conditions just in the presence of
Yeah.
proline by itself.
Which is why I think that product does work so well in the summer. Talk about and I'm not going to even know their names, but I remember you telling us a number of times there's a list of the amino acids. There's three or four that start with a, I think maybe it's a G. Maybe I don't know what the hell I'm talking about. But there was a list, it was on the left-hand side of that column,
Ah,
and you highlighted those as really the most prominent. I hope I'm making sense and you can follow me, or I'll just change the subject.
oh, I need my chart in front of me.
Yeah. There,
Guanine, if I remember right.
guanine, it
That
was the
was at the
G's.
top.
It
That
was
was
the
at the
G's. So
top.
there's three or four G's that
Yeah,
start with the
and
letter
what's
G.
interesting is they actually get synthesized. They become precursors to things like glutamic acid.
Yeah.
That provide a lot of stress resistance.
Yeah,
And proline is one of
that
those
was
that gets
fascinating to me.
synthesized.
And again, I here's another area in our industry that most people, and I'll say I'm one of them. I might be a little bit, more dangerous than others, but amino acids are one of these things that you hear a lot about it. They're using them to stabilize fertilizer. So a lot of manufacturers saying, "Oh, I've got amino acid technology," but they're not really explaining it well, and they're not really bringing to the table the complexity that we've been able to do with the work you and I have done together. And
Mhm.
And I find it, it's another one of these areas that I think can be very confusing. So what's the basic function of an amino acid in the soil profile?
Well, let's say now that it's summertime and they're under stress, it is to actually reduce reactive oxygen species. That's one of their big
ROS.
roles under these stress conditions.
Yeah.
ROS
Yeah, which is happening every day right
every
now.
day, right now. Yeah.
Yeah, which is kind
And
of
if
crazy.
something can be, if these bacteria and fungi can figure out some way of checking that, they
Right.
will do it.
Yeah.
They got to have the diverse inputs in order to do it.
Okay, let me go back to why we're here because I'm rambling and you're wonderfully informative. We started with green, which is the most ligneous, the rootiest, if you
Hmm.
will. Now we digested through microbial breakdown and enzymatic breakdown, and now we
Yeah.
have what you're calling brown
Hmm.
organic matter. What
Hmm.
is it? What's its value? What's pros and cons of brown, and where do we take it to the next? And how do we
Yeah,
take it
at
to the
that
next level?
stage, let's say we're in the transition period between unstable carbons that are being utilized and eaten and so forth. And then at this stage, the carbons are becoming more complex. They're starting to actually interact with each other. And you have a kind of it's sort of a alphabet soup at
Yeah.
this point of things that are either liquid or solid. They can be in a lot of different, they can be in either state. And now they're starting to react to each other. And the color literally turns to a darker color, usually a brownish color. We see this in soils that are going through this process. So it's a combination of things that are breaking down at this point. And the next step is they will recombine with each other and then form extremely what's called recalcitrant carbon, which are extremely complex carbons and very stable, and they're almost black. They're so dark that you could almost call them black. That I just described the humification process right there.
Yes, you did.
Yeah,
So you just went from brown into dark or
yeah,
black humus.
yeah.
So and all of that is microbially generated.
Driven. Yeah.
And what's the so when we're at the dark or what black or dark stage, is that the final breakdown? Is that humus? Is that material that's available to microbes? Talk
Well,
about the dark.
humus is defined as everything that's going through every stage that there is.
So it really has a little bit of everything in it, doesn't
Yeah,
it? Yeah.
that's kind of in the middle.
Yeah.
Now, the final breakdown products should be humified materials, which are extremely stable. They're not eaten by anything. They're broken down rapidly by urea, but otherwise they can persist in an agricultural soil or a natural system for over 10,000 years at that point. But when you hit them with highly soluble nitrogen, that's it.
They're
Game
gone.
over.
Yeah.
It destroys them.
So I mean, and I don't want this to sound completely negative, but in our world we do use urea because we do need
Mhm.
to keep grass growing and pushed and stay. I mean, we're trying to
The
create.
problem with urea is it takes up a lot of water when it goes through the
Yes, yeah,
and, and if it's a little on the alkaline side, guess what one of the byproducts is? Bicarbonates. Oh,
yeah.
lovely.
Sealing the soil surface. But
Yeah.
we can still maintain, we can still move the pendulum in the right direction, even if we do some damage. I mean, the golf course environment, and you know this, the golf course environment, by nature, there's a lot of damage being occurred, physical damage, people walk, I talked to a
Oh,
superintendent that
stress.
had 75,000 rounds, players walking over 3 acres of greens every
Wow.
single year. I mean, that the physical compaction pressure and all that stuff. And in order to
Mhm.
keep any kind of activity, we're going to use some synthetic fertilizer, but it's still a balance of carbon to nitrogen. So by
Mhm.
pushing the pendulum to the wrong side, we can bring it back by making sure that we're maintaining a carbon to nitrogen balance. And that seems to be really coming through in our industry. I mean, I say this at all my meetings now. I think for the first time, I can comfortably say I don't know a golf course or a sports turf manager that doesn't have something in his shop that isn't carbon based. Humic
Wow.
acid, a fish, a kelp, a molasses, something,
Mhm.
that has some level of carbon. And I don't know a single liquid manufacturer anymore, and there probably is some that aren't using some level of one and the same, a carbon material, and mostly to make their products work better. I mean, that's really what's happening is that they're actually seeing, wait a second, this is making my product work better, so I'm more competitive, I've got a better edge. And, this is going back to what you and I've been talking about for 40 years. You longer than me, of course, because of
Well,
my
every product ever made had some kind of humic substance in it,
yeah. So I mean, think
without
about it.
exception.
And and that has definitely changed. So, let's talk. I mean, one of the things that I see, and I shared with you that picture, and what you did is you took it and you wrote, dispersion, carbon dispersion, if you remember
Yes.
this slide. So
Mhm.
I use a slide in my talk, and I show it to a group of superintendents, and I ask them the question, and it might be 4 inches deep of what potentially looks like thatch, right? It's organic matter. It's not thatch. It's actually very digested organic matter, or I'll call it humus. And when you looked at it, the first thing you did, and then you highlighted, you called this the disbursement of organic matter. Explain that thought process when you
Yeah.
saw that. Do you remember
Uh,
what I'm talking about?
yeah, you had a very contrasting slide in
Yeah.
addition that you
Yes, I had
call
the thatch cake.
Thatch cake. Now, those are two wildly different,
Wildly different.
yeah, visions of management.
Yeah.
On the one, they're stacked up, stacked up, stacked up, where you could just simply say, "Oh, undigested, undigested."
Yeah.
Then they do
Well,
a
no,
little.
it was undigested sand, undigested layer of sand,
Uh,
undigested thatch layer of sand. So they were
exactly.
pounding the soil with a lot of synthetic nitrogen and then just
Mhm,
trying to fix it by top dressing over it. But the thatch was so
mhm.
dense that the sand couldn't even penetrate it. So it was not
So,
dispersing
yeah.
effectively, and there was obviously no or very little biology in those layers
So
of thatch.
someone might look at that second slide where you can see this brown on top and gradually getting lighter, lighter,
Yeah.
lighter, lighter. A continuum of brown color going down and it obviously has moved through the sand. It's not layered. It's well dispersed. Now, someone might get the impression that could be called liquid carbon or soluble carbon.
Yeah.
That would be very misleading. What's
And I
going
hear that
on?
comment a lot. I hear soluble carbon, and I'm not even sure I understand what it
First
is.
time I heard it was in turf. What'd they call it? Soluble carbon?
Soluble carbon. Yeah.
I'm
Well,
like,
I mean, that's to
what's
me is
that?
sugars. Sugar?
Sugar?
Yeah.
Yeah. Oh,
I mean,
molasses.
I think, and I'll defend whoever might say this. I think they're really talking about available carbon that would be food sources for microbes to proliferate,
Oh, that could be.
proliferate microbial
Mhm.
populations. It's not soluble, but it is available. I mean, I think we're arguing semantics at this point, but
I think that what's going on there is that these microbes are moving this stuff around. Something's moving it, and then it's breaking it down to such small particulate matter, even water movement through there will start carrying that away and dispersing it. So there's probably a lot more going on there than we realize, but it is nonetheless really interesting to see.
it's in a and again we're seeing great changes. But let's get back. So we went through brown. Brown is still going to digest. So brown is kind of in the
Mhm.
middle between a finished digestion and the starting point of digestion, if that's a fair analogy.
A lot of enzymatic activity going on.
Lots of things going on. What
Mhm.
restricts the breakdown of brown? I mean, what happens, I mean, if we get stuck in the brown
Mhm.
of these three models, what are we seeing? What's a turf manager going to see if he kind of, I mean, sees that kind of stop, and how do we turn it back on?
At that point, they need a lot of complex inputs, and much of that is coming from the exudates. We can add something into a product that'll help that diversity. We already
Hmm.
touched on that. We have more than 20 amino acids in there alone. We have more than 70 elements, just an elemental analysis alone. All of these things can be utilized by the microbial system to do their work. And the other thing we're not doing is disturbing it through what's called chaotropic or actually water, destructuring the water to the point where it's ineffective too. And so we watch the balance of chlorides to calcium.
Hmm.
Chlorides get a really bad rap, but they can go either way. They can be chaotropic or they can be cosmotropic. They can go either way. They can be good or bad. They're right in the middle in what was called the Hofmeister series back in the 1870s when he added different things to egg albumin to see how they disrupted protein, egg albumin. And the chlorine's right in there. So if you have little, if any, bioavailable calcium, chlorides become very nasty. But
Yeah.
if you can counterbalance it with something that's more bioavailable, something that's less chaotropic, then you got a pretty good system going. I pay a lot of attention to that when working on a product. I would Potassium is actually chaotropic. It's very disturbing.
Explain
Chloride.
chaotropic. We're using that term,
Oh
but
yeah,
let's
this
explain
this
that.
guy Hofmeister took egg albumin and he dropped different things on it to see what caused the hydrogen bonding in the proteins to break up and to unfold. Now proteins don't work. When proteins unfold, they are bad. They are
Right.
ineffective. And this guy tested all kinds of things, and calcium was on the cosmotropic end, which means it actually helped build protein. Chlorides are right in the middle, and then the nasties come in, and you got to be really really careful how you balance them against the other things. So it
Goes
was
back to
really an
balancing.
interesting experiment,
Yeah.
like 1875 or something like that. Yeah, the
Yeah, and yeah, the
Hofmeister
information's
series.
there if we just have to know.
Yeah.
Explain to us, you keep using this term bioavailable calcium. How do we get
Okay.
that and what is it?
If you put, let's say, uh, um, calcium sulfate down or calcium carbonate down.
Limestone or gypsum?
Yeah, and you think you're getting a source of calcium. You're not. You are to a degree, but the calcium is not complexed with carbon in any way whatsoever. It's just straight mineral. And when that does break down or dissolve, then it becomes an ion. The calcium is now an ion floating around going, what can I lock onto? It could lock onto a nitrate, for example. Now
Right.
yeah, easily it could lock onto a chloride, and it does, or a
Or a
phosphate.
phosphate. Yeah.
Phosphate is the big one. That's
Yeah,
how
of course.
calcium gets tied up because there's nothing there to buffer this process. And the way that's done in nature is that calcium needs to be associated with some kind of carbon in order to be effective.
So how can we do that in management? How do we get
Um,
bioavailable other than spraying Calvantage, obviously, but that's a cheap shot to sell some
cheap
product.
shot.
But you and I have worked on, well, I should say you really worked on tweaking that product
Yeah.
to make it more bioavailable because of all the
Mhm.
carbons that we are bringing in there.
Mhm. One of the calcium sources in there is calcium nitrate, which I got pretty upset about
Yeah,
because nitrates are very chaotropic. They're very disturbing to the structure of
yeah.
water. That's why they leach. That's why nature says, get rid of those things. I don't want them. Dump them in the Gulf of Mexico, just anywhere but here. Yeah. And I knew I was dealing with a very powerful chaotrope there, but the industry wants to see calcium nitrate in there. So I ended up dropping the calcium nitrate level down in the product, substituted some other calcium products, which I probably shouldn't mention what they were
Yeah, let's not.
because they're proprietary. But anyway, I was shooting for a more benign balance of the source of calcium, a calcium that would actually be chelated by humic substances rather than being battled by a nitrate. And now it's ready. Now it's in a form that can be exchanged with biology. Now it is becoming bioavailable rather than pure solubility.
Yeah,
Calcium nitrate is extremely soluble, but it's very disruptive
yeah, yeah,
also
it can be
to
effective.
natural systems.
There's some products out on the market now that are combining calcium sulfate, gypsum, and
Mhm.
humics. So they call it a black gypsum.
Yeah.
Is that providing enough bioavailability to really make anything happen, or do we still need to bring to the table maybe taking that and mixing it with, a granular replenished fertilizer or something? I mean, is there enough pop from a black, a humic gypsum a blended humic acid and gypsum
Mhm.
product to give us that level of bioavailability?
That product works really good in agriculture, but it doesn't work nearly as good under turf conditions, which is really
Because
different. No.
why?
Well, it's just the biology.
Yeah, just
You
not
have
enough of it.
so much more diverse
Yeah, yeah,
biology in these regenerative agricultural systems.
Yeah.
They're doing everything they possibly can to generate more biological activity. Whereas you guys need a solid surface. You need a short piece of grass. It's called overgrazing in regenerative agriculture.
Right.
So you're overgrazed.
Yes, we
You
are.
got
We graze
compaction.
every day with a mower.
Yeah. I mean, you got the compaction. You got all the things going against you there. You got traffic. You got all these things going against you. So you got to come in with some more calcium that supplements the base. The base idea is pretty good, I think. But you need more than just that going on.
Yeah. You know, we
You,
still are heavily criticized, and there are still some lots of folks in our industry that'll just say calcium is not important.
that's what Dr. Steyer told me about 20 years ago. And boy, did he change his mind after we hired him to do a field trial for us. He started sending me photographs. He got so excited.
Wow, look, calcium actually has something to do with
Yeah,
building
I,
turf.
I sat in on one of his presentations in Des Moines, Iowa before we hired him, and he's like, "Poo poo calcium." I mean, nah,
And that's still
grasses
going
don't
on
need
20
calcium.
years later with some of these
Boy, did he
dinosaur
change his mind. He started
academics.
sending me photographs of the dollar spot going away. We have dollar spot in Wisconsin. We have these very moist mornings,
Yeah, yeah.
heavy, heavy
Well,
dew.
and yeah, a lot of golf courses we have. I hate to tell you this, my friend, but we could do this every week and for hours at end. I always enjoy sharing information or actually stealing information from you. And I think this is an important topic. I appreciate, the review on the humic acid, but again, I think there's a lot of confusion as to what the digestion process is.
Yeah,
And it is biological, and the enzymes that are coming out of that whole process that are, it really is extremely complex, isn't it? I mean, the stuff
very.
that goes
Yeah,
on under our feet, and the reality of it is, we don't really need, certainly a turf manager doesn't need to know the complexity of all this. All they need to do is set the stage. And, that's where like I said earlier, I'm a little scared that the industry might go to, oh, I've got a silver bullet of spraying this enzyme that will eat up all the thatch. But if it doesn't have the support mechanism to be, truly sustainable and allow the soil to be a part of this process, I think we're just going to spin our wheels and go backwards. I think what we've been talking about with Jerry, excuse me, what Jerry Bernetti really put into place so many years ago is a systems approach.
yes. Mhm.
And on that, I'm going to end our podcast. Very well said. Thank you so much.
Thank
Uh,
you.
folks, if you aren't a subscriber of the Earthworks podcast, please do. I promise you, we will have Lawrence back multiple times. I think we try to get you back at least 4 times a year, and I think we've been stealing you maybe more like 6 times a year, but it's always informative. As I said, at the GIS trade show every year, people will come in and say, "Is Lawrence here?" Sorry, Lawrence isn't here. We don't let him out of his building, and but we do bring him on the podcast often, and we get the pleasure of being able to work with him on a fairly regular basis. So, and as I've said many times, every time you talk to us, somebody holds up a sign that says "Record this" because it's just so much stuff. And what I found is that people will call me and say, yeah, yeah, I listened to that Lawrence thing, man. I had to listen to it like 5, 6 times because I just kept missing so many things. I think you came to the table full guns a blaring today, and I did get your dander up, which I'm very proud of. So, thank you, my friend.
Welcome.
I will always be grateful for all your support and your friendship all these years, and we will be back talking to Lawrence Mayhew
Okay.
again soon. Thanks.
Welcome.